Hello and welcome back to day 5. So far, so good. We have another interesting problem today, so let's go ahead and jump right in. Day 5, print queue. Satisfied with their search, the scholars suggest subsequently scanning the stacks of Subbasement 17. Printing department is busier than ever. Okay, Elf must recognize you. They waste no time explaining the safety manual updates won't print correctly. Failure to update safety manuals would be dire indeed. Safety protocol clearly indicate that new pages for the safety manuals must be printed in a very specific order. XY means that if both page and X and Y are to be produced, X must be printed at some point before Y. All right, so there's the page ordering rules and the pages to produce in each update. So there's the sample data. An interesting thing you'll notice about the sample data today is, this is a very common thing you'll find in Adventive code, is that we've actually split the data up into two sections, separated by a blank line. So when we write our parser today for the first time, we're going to take into account that. Okay, so this is, if you're going to print 47, must come before, stop that, must come before 53. Going to print 97, must come before 13. Is there any way to turn this bar off? Really? Whatever. I'll figure that out later. Okay, so those are the instructions, and then we have pages to be printed. Okay. Page ordering rules, before and after. Doesn't necessarily mean immediately before. Other pages are allowed to be in between. Okay. Second section specifies page numbers of each update. Okay, get the printers going. Identify which updates are already in the right order. Well, that's interesting wording. Already in the right order. It implies we're going to have to fix some later. In the above example, the first update is in the right order because 75 is good. It's 47, 61, 53, and 29 all come later. 47 is good because 47 is after 75. And okay, so yes, so we apply the rules. Because the first update does not include some page numbers, the ordering rules involving those missing pages are ignored. Second and third updates are also in the correct order according to the rules. Like the first update, they also do not include every page number. Okay. So 7597 is wrong because 97 has to come before 75. Okay. So we have 3 that are right and 3 that are wrong. Is that right? Yeah, 3 that are right and 3 that are wrong. So, for some reason, the elves also need to know the middle page number of each update being printed because you're currently only printing the correctly ordered updates. You'll need to find the middle page number of each correctly ordered update. So 61, 53, 29, that gives us 143. Okay. Need to be careful. The actual list of page ordering rules is bigger and more complicated than the above example. Determine which updates are already in the correct order. What do you get if you add up the middle page numbers of those? Okay. So we have our task, right? Let's see if we can sort of restate what our task is, which is we need to parse the before-after rules. We need to parse page requests. Ensure pages are not illegally placed. And return the sum of the middle page of correct printings. Okay, so that's pretty good. So let's do we're going to call this a parser. Why not, right? Simple name for things. And we're going to start talking about the parser class and parser tests. Public void. So what's the simplest thing we could do? We could say valid print request. Okay. Let's say we're going to make the parser with the list of lines from our file so that we don't have to read files here in these tests. So this is just going to be an array of text, right? So we'll do this to say 1 and 1 must come before 2, and then we have a blank line, and then we ask to put 1 and 2. Actually, we need the middle, so we want odd numbers of pages in our instructions. That wasn't necessarily what they said, but if you look at the data, that's always the case. We have odd numbers so that the middle is unambiguously known, right? All right, so this is okay. This is what we understand to be okay. We want to do parser dot verify. Let's see. We'll just do verify. That's what we'll call it. Okay, and it's going to give us back the middle page number of verification. So that should be equal to 2. Okay. And then for an invalid print request, which will be our next test, we're going to have 213. And for that, we'll get back 0. We can skip this for the moment because this is just coming soon. All right, this is the one we actually care about. Let's make sure we skip this as well. Not yet. Okay, so we have 2 things we need on the parser. First thing we need is a constructor. So we'll take this as lines. And then we're going to have to parse that. And then we're also going to need public int verify. And then for this, we will throw new not implemented exception. Okay. So for now, this test should fail, right? Because of course, we're not doing any parsing. We're not looking at any of the stuff. Okay. So far, so good. Let's just take it as assumed that we could return 2 and make this test pass. We've shown that a couple of times now. We don't need to keep doing that. Although it is a valuable thing to be able to do, to be able to force yourself to implement the correct algorithm by ensuring that you have enough tests to make it happen. But we're going to know that we have the algorithm implemented correctly because we have the real data to test it against. So that's good enough. So we talked about how the data here is split up into 2 sections, right? So we're going to look for the break index. That's going to be lines index of string empty. And we don't have index of because arrays don't have index of. But if we turn this into a list, it will. Okay. And then we need to know the the instructions for the requirements, and then the page list. So then the first thing we'll do is we're going to do for each var line in lines up to the break index. All right, that's going to be the first section. And then we're going to do another for each, which is line in lines after the break index. Okay, so that's our 2 sections of stuff. Now, we haven't really talked about the best way to think about how to do this. We really need this idea that when I see 1, I need to go and make sure that I walk the rest of the list and make sure none of those numbers, I'm sorry, yeah. I want to make sure none of those numbers are in the before and after, right? So we have before and after. So actually 1 has to come before 2. There's no requirement about, actually where this is. So what we're actually interested in is when we see 2, we want to make sure we don't see any 1s after 2. That's really sort of the crux of this problem, right? So we're going to look at 1, and we're going to say there's nothing that 1 has to be before. So that's okay, right? And then when we go to 2, we say, okay, well, 2 has to have 1 not after it. You can think of 1 has to be before, but really the way we're thinking about it is 1 is not after it. So we're just going to walk this list and then look through that stuff. So the easiest way for me to think about doing that is I'm going to keep these prerequisites lists. I'm going to keep it in something like this. Read only dictionary of int to hash set of int. Prerequisites by page. All right. So that's where we'll start. That's going to be this first half. So pieces, of course, we do a line split on the break, and then we say, I'm going to cheat here, and I'm going to use a function that I love. That's an internal function in XUnit. You'll see what I'm going to do here, right? So our prerequisites is prerequisites by page dot get or add. Sorry, is it add or get? Yes, add or get. And what this does is we will pass. We're going to pass the right-hand side, because the right-hand side is the one that has the prerequisites, right? So when we look at this rule, we say the rule is for 2 that you have to have printed 1 first. So, or you can't try to print 1 later is another way to look at that. So the index into our dictionary is going to be the right-hand side of this. So what does this add or get do? This returns, what this does is basically says, if you don't, where is it? If you don't add or get, yes, add or get the value. Go ahead. I don't know why it doesn't want to come down here. It does this little quick thing here, which is if I couldn't get the value, then I go ahead and I make the new value, and then I put it in the dictionary, and then I give it back to you. Super handy for when you have a collection on the right-hand side. It's like, I don't care whether you had this page in there before or not. I want to get a hash set that represents all the prerequisites for that page. Let's find out why we're red. Type arguments cannot be determined, can be inferred from usage. Oh yes, this has to be, these have to be converted into ints. Okay, that's why we couldn't figure out the usage. And then we're going to just go ahead and add pieces sub 0. Right, so we're going to add the left-hand side of that and say, whenever I see page 2, a prerequisite is page 1. Okay, so that's the first half of our parse. So the other half of that parse is we just need these instructions, which are separated by commas. So we're going to call these page groups. So we're going to do a list of the list of int page groups. Okay. And then for every one of these, we're going to say page groups add. Line splits on commas, and again, int parse these and turn this into a list. All right, and then that's it. That's our parsing. Not too difficult here today. So when it comes down to verify, what is that going to look like? Before we do that, let's come up here. We'll set a breakpoint here. I like to just kind of like peek to make sure that there's code that's not being used. Let's get rid of all this stuff. Let's get rid of all of this stuff. Who knows what is up with that? Let's do call stack. I like call stack better. Okay. So now if I come up here and I look at my prerequisites by page, we'll see that we have 1 item in there, right? 2 has 1 prerequisite, which is 1. And our page groups, we have 1 of those, and it looks like 1, 2, 3. Okay, looks like we parsed it all correctly. I'm happy with that. This test is, of course, going to fail because of the not implemented exception, because we're not there yet. So how do we think about verifying this? What we do is we walk through the list. Let's start with for each var page group in page groups. Okay, we're going to walk all of those. Var results. We know we're going to need to return the results, right? Okay, so for each page group, we're now going to say for each var page in page groups. Although we really kind of want the index. So let's convert this to a 4 because we actually want the index, right? Page index. So that's our page. We want to now take a look at that page and look for any things that need to be printed before this page and make sure that none of those are in the list after this page. That's why we're going to need this index, right? So we're going to say if the prerequisites, because not everybody has prerequisites, right? So we're going to try and get the prerequisites for this page. And of course, I forgot a parenthesis, as is my wont to do. Page is not null here. Cannot convert from a list page group. Yeah, this is supposed to be group, not groups. Okay. So we're going to go look for the prerequisites. If there are prerequisites, then what we're going to do is we're going to look over. Let's see, remaining. We'll take the remaining pages, right? So the remaining pages as an int array, or as a list of an int, whatever. Remaining pages are going to be page group sub page index plus 1, right? So that's the remaining pages. And we're going to go for, we'll start with a for each just in case, but I think we're going to need a for here. For each var next page in remaining. Okay, if the prerequisites contains that page, contains that next page, then that means we have violated the rules, right? So what exactly does that mean? That means that we can't count this, right? This isn't valid, so we need to return 0 out of that. If we wanted to break, the interesting thing is we break here. We really want to sort of break out of here. So I kind of, in situations like where I want the flow of control to be better, I'm going to extract this out into its own function, right? And we'll call this verify, public int verify for a page group. Okay. We'll throw that there. And then we're going to say result plus equals verify for the page group. All right, and then we can return the result. And of course, if you ever see a pattern like this, where it's like, oh, I'm going to run over a list of things and then I'm going to add them up, I can easily turn this into page groups select. For this page group, I want to verify the page group. And then I want to sum them all. That's it. This code down here is exactly what that code is up there. And of course, even better, we don't need the lambda. Okay, so this isn't actually going to be public. This is an implementation detail. So now we've got, again, we're looking at one page group. So if we break the rules here, then we can now just return 0, right? We know this page is broken. So if we find a page here that is broken, we can return 0. If we go all the way through this loop, what we should then find is that we can then return page group sub page group count divided by 2, right? We're going to return the value of the middle page. So what is this loop doing, right? We're looking over every page in the group, right? If that page has prerequisites, then we're going to look through the rest of the things in the list. So going to the right, if we see any of its prerequisites on the right, obviously this isn't good. So we will bail out of there. Okay, let's take a quick run at this and make sure that this is working. Okay, so good. Coming soon, right? And we've also implemented, I know we implemented a little bit too much by doing our return 0. But we've also implemented our case here where we've identified a pattern of 2 doesn't work because the 1 prerequisite is sitting over to the right. Okay, So that's pretty much it. We don't even need a 3 there, right? We can even do 1 and 2. All right, and those should still pass. Okay, so that looks like it's doing a pretty good job of what we're after. So we now have parse before and after, parse page, page, page. Ensure pages are not illegally placed, return the sum. I think we're ready. Right, so if we're going to say our parser is a new parser, given file, read all lines from our file name, we need to turn that into a list, right? And then the result, I don't know why I deleted that, result is going to be parser dot validate. What do we call that? Verify. Parser verify. That's going to give us the numbers from all the valid pages in the middle, right? Oh, and we're still skipping, so that's not helpful, is it? Okay, so that looks pretty good. Now we have our big giant data set, and as you can see here, as we run through this, we have a lot of prerequisite rules. It's always good to sort of look over this data. We can see all the page numbers are 2 digits, which is interesting. So there you go. We have 1,176 prerequisites. That doesn't sound like too big a number for us to have in memory. Seems pretty good. And then we start from 1178 all the way down to 1385. So it looks like we've got about 200 page sets to run through to validate. Okay, so when I did this last night, I came up with 5275 for this. So let's go ahead and test our implementation and make sure that that's good. And it is. Okay, are we happy with where we landed? I mean, obviously we should be writing more tests here, but let's actually do that, right? So if we do a mix, let's do a mix of stuff. Let's say facty public void mix of valid and invalid. Okay. So if we have rules that say 1, 2, 2, 3, and then we have a print request for 1, 2. Oh yeah, that's right. Now I remember why we had the 3 there, because we need odd numbers of pages. Very good. All right, so if we have 1, 2, 3, 2, 1, 3. Let's see. Given these rules, there's not a whole lot of other ways I can put this in here. Whoops. We can put in here like 1, 5, 6. We haven't seen 5 or 6 on either side. So we know this one is valid, so that's going to be 2. We know this one is valid, that's going to be 6 or 5. So 2 and 5 is going to be 7. I mean, given that we tested with the big data set, I don't expect these things to fail, but you know, this is, if we were doing this for real, like we'd have a decent number of tests that sort of evolve out of the design of the algorithm, and we would follow the pattern we did earlier in the week where we were showing, you know, it's like, okay, start with just returning 0, start with, you know, just whatever. Sort of evolve the algorithm as you go. The reason that I knew that I wanted a dictionary event to hash set event is because I did this already. And I wanted to, you know, skip ahead a little bit and save you some time. But this isn't necessarily the only way to implement this, right? You could come up with another way to implement it. That would be, you know, on you to decide if that's how you wanted to approach this problem. Okay, so now we need to go look at part 2. So let's go hang out with part 2. While the elves get to work printing the correctly ordered updates, you have a little time to fix the rest of them. For each of the incorrectly ordered updates, use the page ordering rules to put the page numbers in the right order. Okay, so the 3 that were wrong, here are the 3 incorrectly ordered updates and their correct orderings. After taking only the incorrect ordered updates and ordering them correctly, their middle page numbers are 47, 29, and 47. Adding these together produces 123. Find the updates which are not in the correct order. What do you get if you add up the middle page numbers after correctly ordering just those updates. What they don't say here, but I can tell you from doing the puzzle, is that the idea here is that you need to, here we're swapping 75 and 97, right? So we have 97 and 75. And here we're swapping 13 and 29, right? And here we're swapping, we need 29 to come after 47, and we need 13 to come after 29. So the idea here when you iterate on this is that, first of all, we have more than one change possible necessary here, right? Because this one takes 2 changes. And so what you generally are going to end up doing is here, when you find a page that is out of place, what you're going to do is you're going to put it, so like let's say 1 depends on 2, and you have 2 comma 1. You're going to put 1 immediately before 2, right? That is the unwritten rule of what's going on here, because in theory you could put 1 all the way up at the front if that's what you really wanted to do. So in general, the strategy that we're looking for here is a recursive one, where whenever we find a broken page, right, we're going to order it so that it is in the right place optimistically, right, and then rerun the algorithm again. Because, like I said, down here in this case, we definitely have to move more than one page, right? 47 and 29 need to get flipped around, and 13 needs to end up at the end. So how do we do that? We're going to just take this and put this down here because we don't know exactly what this is going to be yet. But we want to take the data that is in there, and we want to take the data that's in there and sort of flip it around. So what's the first version of this that we can think of, right? So let's say we have a valid print request, valid print request already, valid print request, but this is for, what do we want to call these? Only fixable. Call this only fixable, okay? So what if we had, for example, this thing which we said only fixable is true. Whoops, only fixable is true. What if we had a flag here? Well, if we already have a good print order, then the result should actually be 0, right? And then if we have an invalid print request, right, or only fixable, right? What is it? What is the actual order going to be here, right? It's going to be 1, 2, 3. And so for 1, 2, 3, our answer should be 2. So we'll go ahead and skip this again with coming soon. But these are the 2 cases that we're sort of interested in fixing here. So we want to update our verify function to say, really only show me things that are fixable. So obviously we're going to need to pass that along. Page group, verify page group, only fixable. Okay. So really what happens here for us is, what do we do here, right? Because right now when we find something that's broken, we just say, well, that's it, it's broken, return 0. But in the case where we want only fixable, we want to try and fix it and then return its value, right? I will tell you that everything is fixable, right? They didn't give you anything that wasn't fixable because then you'd be in a forever loop. They aren't that mean on day 5. Putting you in a forever loop is definitely something they'll do later on in the series, but not today. It's just still day 5. So everything is fixable. Okay, so the first thing we can say is if this is not if the prerequisites contains the next page, right, then what we want to do here is if you're not only fixables, then you return 0, right? If you're fixable, then what do we do? Well, we need to know exactly what the value is that violated it and where it is. And we need to slice the array up to put that value just before the thing that requires it, right? And the thing that requires it is the page. So this for each isn't really gonna help us. So let's go ahead and convert this to a for. And this is going to be the violator index. That's what we're going to call this. Okay, and then this is the violator, potential violator. I mean, we'll be nice about it, right? Potential violator. So now what we need to do is, given that, we need to make a new list event, new pages, right? And we're going to use our magical ability to stitch arrays together. So what we want is we want all the pages just before page index. So that's going to be page group up to the page index, right? Then we're going to need to put the violator in place. Then we're going to need the rest of the pages. But remember, we have to take the violator out. So we have two sections, right? We have the section between the current page and the violator, and then everything after the violator. So that would be the page group of page index +1 up to the violator index, right? And then we have the page group from the violator index on to the end. Okay, well, we've got a bunch of things in here, so let's do this so we can see what's going on here. And that was obviously not what I meant there. That is what I meant there. Okay. So everything from before the page, current page, into the new pages. Let's just see if our logic is good here. So we'll go ahead and run this test for our first piece of data. Only fixable. Oh yeah, let's do only fixable is false. We'll give you a default value so that our other test don't change. Okay. 2, and we expected 0. And we never got into our only fixable, so that's interesting. Yeah, why didn't we hit here? Yeah, okay, that's weird. All right, well, let's try and put a test here. I'm going to run just this one test. So let's run just that one test with Test Explorer. Yeah, that's interesting. That never comes into only fixable at all. Or never see a violator only fixable. I don't understand that. So there's our page group, only fixable gets passed in here, only fixable. I mean, obviously we're hitting here, right? Let's see if we can figure out where the logic bug is. Let's run just you, valid print request, only fixable. Oh, am I running the wrong one? Maybe I need to run this one. Yeah, that's the problem. I'm running the wrong one. I'm going to keep you over there. Okay, and my guess is now I'm going to set this down here and everything's going to be fine. Yeah, so there we go. So let's take a look at what our new pages looks like. Oh, we have an argument out of range. That's interesting. All right, so page index. So let's take a look at our page group. All right, so we have 213. So what is our page index? What is our page? Page is 2. What is our violator index? What is our violator? Our violator is 1. Okay, so that makes sense. The violator index being 1, remaining. Right, okay. So we want to see the remaining. Isn't that interesting now? We have, I see. Instead of making a remaining list, because we're not using link anymore, I see what's happening here is our indexes are off. We'll just say the violator index starts at page index plus 1. And then that is page group count. And we'll pull that from page group. Okay. All right. So here we are. We don't have remaining anymore. That's not a thing. So our violator is 1. The violator index is at 1. So this, so page group of this, right? Let's go into our immediate window. All right, so that's nothing. That makes sense because there's nothing before 2, right? We know what the violator is. So what is this? That is also nothing because the 1 comes immediately after. And then this should contain the 3. It does. So when we do new pages, what we should then see now is 1, 2, 3. Oh, 1 and 3. Where'd our violator? So our violator. Oh, yeah, we need to do. We actually. I see. This is not plus 1. Okay. So if I do this again, that's where our 2 came from. That's why our 2 was missing. So we want all the pages up to the problem. We want to insert the violator just before the problem. We want all the pages, including the problem, or including the page that is that we're trying to fix, all the way to where the violator was. And then we want everything after the violator. So our new pages now should look like 2, 1, and 3. Okay, so that's good. So we now have our new pages in the right order. But we need to run the algorithm again. And what's going to happen here is if I say return verify, only fixable, let's see, our new pages with only fixable, right? Then we have a problem here, which is as soon as it's in the correct order, right now we're going to return 0 because it's only fixable, right? So that is, oh, sorry, actually, we're going to return, maybe. We'll see what happens here. All right. So that test passes. Does this test now pass? Because that should now return 0, right? Okay, it should return 0, but it returned true. So this is what I was worried about now, is the other half of this. When we ask for only fixable, we don't want this value because it's already fixed, right? Now the problem is if I just like turn this into, you know, if not only fixable, and we return that, right? Otherwise we return 0. That's going to break other things, right? So that's still giving me a value I don't want, right? Because I end up down here with 0. Because what ends up happening is we come all the way through the loop. We've fixed it now from 213 into 123, but now we actually want a value out of it. So that means in order to know whether or not we're going to return a value here, we also need to know whether or not we mutated things, right? So we need another flag here, which is mutated. Did we mutate this? All right, and we'll start that out with false. And then here we'll say true because we have now mutated the thing. So we're going to say if you've mutated or you're only fixable, then we will give you a number vec. Okay. So does that make sense? We only want a value when we have fixed it. That's why we need to keep track of whether or not we've mutated it or not. If it comes all the way through once and never mutates, we don't want that value if you said only fixable. If you go all the way through once and nothing changes, but we want the regular ones and we want the regular ones. So far, so good. This looks pretty good to me. We've got our values here. Let's see what happens now if we verify this with only fixable now being true. Do we get 123? We do. Okay, that's good. And now, do we get our big number? We do. Okay, so that's kind of an interesting thing, right? I could have written this algorithm twice, once for, you know, only the things that are correct and once for only the things that are broken. Could have written that algorithm twice. Another thing I could have done, now knowing what I know, is up in the constructor, I could have gone through all of these page groups. And rather than just having a list of ints, I could tell you, for example, I could say, here's my values, and did I mutate it to make it work, right? So I could come through here and then basically verify everybody, right? And then if you're not correct, I will put you in the correct order, but I'll note that you're mutated. And then verify becomes simply looking through the list and saying, hey, show me the ones that were mutated, show me the ones that weren't mutated, right? Or fixed, if you prefer, but that's, a keyword. So that's another way we could have implemented it. Basically implementing it all up here in the constructor. Knowing that we're going to end up with correct page groups one way or another, we either have to take them as they are or fix them. Oh, PoE2 preload. Thank you for that. By the way, I'm playing Path of Exile too. So, thank you for that, browser. I guess that's about it for today. I don't have really anything else. I mean, I could go through what this version might look like, but I think that's probably something you could do yourself. I mean, you're basically just going to run this. You're going to run this verification on each page group, and then what it can do is basically, rather than verifying the thing and returning back a number, right? It might be like, it would be something kind of like, I'm going to return you back a list of int, which is the correct page order. And I'm going to return you back a flag, which is, did I have to fix it? Right, which is fix up page group. That would take a list event page group. Right, that would basically do this. And then we would basically run this same loop, except instead of, returning back a verified number here and having a mutated flag, we would know whether or not you fixed it because we're in this part of the loop to say you fixed it. And then otherwise you get down here. When you get down here, you always have something that's already fixed. And so you could return it saying, hey, this is false. I didn't have to fix it. That's about it. I'm going to undo this, but I'll undo that afterwards. I'll leave that as an exercise for you. If you want to evolve this design, take the tests. Write any more tests you think are necessary in order to evolve the design and see how you can refactor everything without having to change any of the code that's sitting there. And that's kind of the essence of refactoring is I'm going to change that production code, but I'm not going to change those tests, right? The tests tell me what I want it to do. And then that refactoring will be, I'll do that. Hopefully that will turn out the way we want. The tests guide us as to whether or not we have done the right thing or not. So if you like doing that, let us know in the comments. Maybe post your own version of the code on a GitHub repo so that other people can see. Or if you come up with an entirely new version of how to solve this problem, that'd also be great to see. So obviously, as you just saw, I'm playing Path of Exile. The early access starts tomorrow. I don't know how that's going to impact this. Probably not. But I am also concerned about getting to the point where at some point it's not going to be interesting to do TDD anymore. Like I said when I did the day 4 video yesterday, it seemed to me like it wasn't TDDable, and I had to go back and think about it and think, yeah, there's some TDD practices that can be pulled out here. But at some point, these problems are just going to be so arcane and archaic that the problem solving is just going to be about the problem solving, and the common code is not going to be that interesting. So don't expect this to go the full 25 days, is what I'm saying. So if this is the last one you ever see, then maybe it starts early. I think we've got a few more days of this stuff, though, before things start to get really complicated to the point where the TDD value will be hidden. But hopefully having, this series of videos has been helpful. So hopefully I will see you next time.